Okay, so back from the break for part two, getting through the rest of this notebook. You have now downloaded and installed a machine learning model that will do things like parse texts into sentences, parse texts into words, give you parts of speech, give you grammatical constituents like the subjects and objects of verbs, and things called named entities, which lets you pick out people, names of places, other things like that. So I'm just going to show like how to do a couple of those things. The idea behind this is that a way to pull a text apart, retaining some of its semantics, so that you can put it back together later in a generative fashion in order to create a computer-generated narrative artifact. So this cell right here is going to do a couple of things. Basically, it's going to go through every single sentence in the corpus. It's actually going to go through 1,000 sentences randomly sampled just to keep it fast, and parse that sentence into words, first of all, and then into noun chunks, which is like every noun in the text plus if there's like an adjective before the noun, like the big school bus would include the and big in addition to school bus. That's a noun chunk. And then also named entities, and then put them into Python lists. One is words, one is noun chunks, one is entities. And then this is just showing like 10 random words. Again, I just like to use this random sample function to sort of like look in the text a little bit to make sure that I have the stuff that I want. But you can see like when you're looking at these random samples, they do already kind of look like words from romantic comedies. Confronts, match, shop, hunter. That's a very romantic comedy name. You can adjust this number, by the way, where it says 10. If you want 100 of these instead, you could do that. This gives us 10 random noun chunks, so you can see what those noun chunks look like. So it's giving you all of the nouns in the text plus any adjective or individual item that comes or determiner that comes before it. So Mauricio, Ellen, a penchant, Forrest, Stephen, Garay, Samantha, Adam, his blindness, Steve, the night, which itself is like I don't know, a weird poetic summary of some non-existent movie. And then 10 random entities. So these are like names of people, numbers, dates, monetary amounts, locations, things like that have been extracted. And we're going to play around with these a little bit later on in the notebook. You can get more granular than this. And I can show some examples of that as well. But I think we're just going to stick with like kind of playing around with these for a second. Right, so I'm hoping that maybe your brain is like going to, oh, this one's weird, eventually Victor. So it's not perfect. In this case, it's like clearly, unless there's a rom-com that has a character named Eventually Victor, which I think is a great character name, actually. But you can see that it's like picked this off as like thinking that it's part of the name, when in fact it was probably part of the rest of the sentence. Another thing that Spacey can do that's like super, super powerful is it is able to parse a sentence not just into words or part of speech, but also to the grammatical roles of the objects of the words in that sentence, right? So the grammatical role is things like the subject of the sentence, the object of the sentence, indirect objects, things like that. So in a sentence like, say, what's a good sentence? The cat chased the dog into the subway station. In this sentence, there's a bunch of stuff that we know about this sentence. We can do a part of speech analysis of it, right? If we did a part of speech analysis, it might look something like this. Zoom out a The word the is a part of speech called a determiner. Cat is a noun. Chased is a verb. The is a determiner. Dog is another noun. Into is a kind of word called a preposition because it introduces another phrase. The is a determiner. Subway is a noun. Station is a noun. I could also put an adjective in this, like the audacious cat, and that would be an example of an adjective. Right? Oh, an audacious and adjective happen to have the same number of letters, so that worked out. So this would be a part of speech analysis. It tells us what each one of these words is doing in the sentence. If we're doing a grammatical role analysis, then we're actually going to break it down into what phrases in this sentence are performing what roles in the meaning of the verb. So in this case, the audacious cat, that whole thing would be the subject. That's the subject of the verb, is the audacious cat. The dog is the direct object. This is not the best way to make a diagram, but there we go. That's usually, in Spacey, that's abbreviated as DOBJ, the direct object. The action is being performed on the dog. And then this part of the sentence over here is called it's called a prepositional phrase. And that might also technically include the preposition, but for our purposes, we're just going to say this. Right, so these are all chunks of the sentence that play a particular role in the meaning of the sentence. And I think like a potentially rich way of approaching a corpus is to do this kind of analysis on the text, to say like, okay, in a corpus of romantic comedies, who are the subjects of verbs? Who are the direct objects of verbs? Where are things happening? Like we could get all of the prepositional phrases and use that as a basis for recombination, right? So I think that this is like an interesting way of recombining texts by breaking them apart into these units. There are other grammatical roles other than just these three, but these are three to start off with. Questions about that idea? I don't know if this is like making people have bad memories of their English classes, but there are lots of other things that you can get. So the name for this in Spacey is called dependency labeling. That's because the way that it parses these into grammatical trees is called dependency grammar, which is slightly different from like maybe the grammar trees or the sentence diagramming that you might have done in high school, or if you took a linguistics class in college, which you should have if you didn't. It's a really cool subject. Here are all of the different kinds of, I linked to in the notes annotation specs. This shows you in Spacey like all of the names of all the things that it can extract, so like all of the different kinds of parts of speech that it can extract. And then also here are all the different kinds of phrases that it can identify, so like conjuncts and copulas and determiners and indirect objects and nominal subjects and oblique nominals. I have no idea what that is. Punctuation is another kind. So these are all parts of the sentence, like parts of the semantics of the sentence that it can grab for you. There's I wonder if this bot is still working. Where did I do this? I didn't expect Deep Space Nine to come up again. I made this Twitter bot called Cheap Space Nine that operates along these principles. If you're not familiar with Deep Space Nine, are people do the kids still watch Deep Space Nine? That's the question that I'm asking nowadays. This is Deep Space Nine. These are the cast members. Very good science fiction show. I think the best of the Star Treks. I like it a lot. It's a rich cast of characters. So I wanted to make a Twitter bot that like recapitulates or invents new episodes. And one way to do that would be to like train a language model like a Markov chain or GPT-2 or whatever. But what I did instead is I took a bunch of plot summaries of Deep Space Nine episodes, parsed them into grammatical constituents, and then swapped out those grammatical constituents in in essentially like a tracery grammar. And you ended up with things like this, where the character names are picked out and then put into new patterns. So Jadzia is assigned to reactionaries. Cassidy Yates promises to provide a diplomatic conference. The problems, however, assist the prophets. Right? So it sort of makes sense. The characters are familiar, but the situations are unusual. That's pretty good. I would watch that episode. Okay. So, and that's an example that does that with the rom-com plots we're going to get to in a couple of moments. So this line right here, when you execute it, is going to go through all of the noun chunks that have already been extracted from a rom-com corpus and just grab the ones that are subjects and the ones that are objects of sentences. So now we can do like a random sample. Here's a bunch of things that it thinks are subjects of sentences. You can see it definitely got this wrong. Or maybe it didn't. It's saying that the to kiss is a sentence, or is a subject, but it was probably like, this was the entire sentence. But you get like boys, Vince's father, Charlie, Frankie, she, he, she, Mrs. Pierce, Katie. So things that were subjects of sentences. Objects of sentences include him, a mauling, weird, the castle, a sexual encounter, marijuana, right? So we already have like sort of like a weird basis for recombining these texts into new text, right? So we have subjects of sentences and objects of sentences. So Charlie, verb, the castle, Frankie, verb, the depths, she, verb, a sexual encounter, Mrs. Pierce, verb, marijuana. If we had a verb in there, we could start making new sentences that were based on this existing corpus. So to do that, we can also use Spacey to grab parts of speech. So this cell right here is going to go through all of the words that we collected and then use this part of speech attribute of Spacey. .pos is part of speech tagging, which lets us get all of the things that are nouns, all of the things that are verbs, all of the things that are past tense verbs specifically, all of the things that are adjectives, and all the things that are adverbs, and there are a couple more that you can get as well. The actual phrases to put in here, there are two ways to get parts of speech from Spacey. One is .pos underscore, and one is .tag underscore. Those are two different ways of annotating parts of speech. One is the universal part of speech tags, and one is the Penn Treebank tags. The Penn Treebank tags are much older and much like better supported. And for some reason, they decided that JJ means adjective. I don't know why exactly, but that's there. If you want the full list, I linked to what I think is an up-to-date link, but maybe isn't. Oh, but it links to the right place. So this is a list of all of the parts of speech that you can grab underneath English. These are all of the .tag ones. So if you just wanted to get all of the superlative adjectives, you could do it like this. So JJS is the superlative adjective. So that's words like best or hottest or tastiest. Why are those words coming to mind? I don't know. Smartest. I'm just reciting to you my OkCupid profile. So the way that I do that is copy that tag, and then I'm gonna like just keep that tag in mind, put it there. I'm gonna copy this line where it says adjectives, paste it beneath, and then I'm gonna say like superlative adjectives, make a new variable name, copy that tag in there, make sure I'm using .tag in this line, and then hit enter. And now I'm going to have like a list of nouns, a list of verbs, a list of past tense verbs, adjectives, superlative adjectives, and adverbs from all of the things that we took from this romantic comedy corpus. And just to, I maybe didn't make this as clear as I should have. This line up here, this is this cell right here is where we actually parsed the sentences from the rom-com corpus. but I only did 1,000 of them because it takes a long time to parse the sentences. If you want to get all of them, then you can comment this line out and then uncomment this line, and then that will go all through all 29,000 of them instead of just 1,000 randomly sampled. But for our purposes, 1,000 randomly sampled is enough. I just didn't want to wait for it. It probably only takes like 10 minutes or so at the most on my computer. On your faster computers, it would probably go faster. But okay, so this is giving us our part of speech, and then this line, this cell right here, just samples some things from one of those lists. So any of the lists that you've defined up here, you can replace nouns with that instead. So I can replace this with verbs. That's going to give me 12 random verbs. I can replace it with past tense verbs. That's going to give me 12 past tense verbs. Past tense verbs are really, really useful in text generation. And that's because they're invariant to the subject of the sentence. In English, normally we have to make the subject of the verb agree with the verb. So it's like, I eat, but she eats, right? In the past tense, you don't have that. English verbs are invariant in the past tense unless it's to be, or maybe others. Have isn't. Go is, though. Go in the past tense is also regular. But for the most part, if it's in the past tense, you don't have to worry about making it agree with the subject. Generating sentences where the subject agrees with the verb is actually super difficult in English, especially if you're doing a corpus-driven approach. So past tense verbs sort of obviate that. 12 random adjectives. These are like such romantic comedy words. Current, lifelong, rich, despondent, capable, short, cocky, correct, several, sour, potential, pregnant. That's actually like a whole plot summary of a very good romantic comedy. Let's see what the superlative adjectives are. Best, best, worst, lowest, best, 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 oldest, least, best, hottest, youngest. Wealthiest. It's almost all wealthiest, youngest, hottest. That's actually super fascinating. This could be like a whole digital humanities paper right here. Okay, and then moving on with this, the other thing we can do is when we're grabbing those entities, so entities are noun phrases that have been labeled with a particular type. And again, in the annotation specifications, which annoyingly they keep on moving around in the documentation, but they're listed here. These are all of the kinds of things that the machine learning model thinks it can recognize in a text. So persons, nationalities, facilities, organizations, countries, and so forth. You can tell that the machine learning model was trained for particular purposes, like the fact that it can recognize like products, right? Tells you that this model was trained to do something very particular, like scrape through Twitter results and see what people think of Pepsi. But we can sort of subvert it to our own uses. So this cell is going to grab everything that looks like a person, everything that looks like a location, and everything that looks like a time from the text. And then this prints out, here's 12 random times that are listed in the corpus. Some of his hours, midnight, a hen night, the next morning, the following morning, the next morning, one morning, that morning, lots of mornings in rom-coms. Lots of the next mornings, specifically. I didn't expect this to be so on the nose, but it is kind of. And you could replace this where it says times with locations. So get 12 random locations: Antarctica, Eden, Santa Catalina Island. Doesn't get it wrong, or doesn't get it right all the time, although maybe this is the name of a restaurant or something in the text itself. No, it's definitely misrecognizing some personal names as as locations. And then people. So here we have just like names of people that are in this corpus. Pardon. Questions about that so far? So again, we're using Spacey's model to go through this text and identify things inside of it, with the eventual goal of gluing them back together in an interesting way. Just for completeness and also to show how you can export this data, the next couple of cells are just about counting things in this text. So in Python, there's a really easy way to count things, and it's the counter object. So you can do counter, and then this little thing inside of here, you can replace anything that we made a list of in Python. So the words, the nouns, the verbs, the superlative adjectives, anything like that, you can replace right here. And then it's going to create a counter, and then you can ask how many times a particular word occurs. So we have 12 meanwhiles in all of the words in the text. How many smiles? There's one smiles. Two occurrences of the word smile. Two mentions of buses. I don't know. More romantic comedy should have scenes on buses, I think. And then this will show the 12 most common words. This is actually pretty interesting. In most corpuses of English, her is not usually one of the most common words. But in this corpus, we found a corpus that at least talks about women and the things that women have fairly frequently. More frequently than it talks about the things that men have, for better or worse. This is showing how to do the same thing, but counting one of those other lists. So if we wanted to count what are the most common people in the text. Oops, what did I do there? Yeah. This tells us that here it's counting the most common. Again, your list is going to be different because you sampled 1,000 different lines. But we have 15 Steves, 12 Kates, 10 Bens, 10 Marys, 9 Beths, 9 Adams, 9 Richards, Frank Droft, Peter, Zach, Joe. It's weird to me that there's only, of the top 12, it looks like only 3 of them are women's names. I don't know what that means exactly for the text. But then you can keep on, if you can just cut and paste this cell and then replace the names of the variables with whatever you want to count. So if I wanted to count those superlatives, I'll do superlative count, and then the variable name that had superlative in it was superlative adjectives. In Jupyter Notebook, by the way, you can hit tab and it will autocomplete the variable names. And then do superlative count dot most common 12. Yeah, so 17 bests, 2 oldests, 2 leasts, 2 youngest, 2 worsts. We would probably get a better list of these if we sampled more lines from the corpus. But that's just to demonstrate how to do it. Most common past tense verbs was had, did, were, gave, asked, called, left, thought, happened, got lost. And then this cell will let you write those to a file, to a TSV. So if you take one of these counter variables that you defined up here, and then run this line, save counter TSV, it's going to save that in the directory of the notebook as a .tsv file. This TSV file you can open in Excel or in Numbers or upload it to Google Sheets, and then use that. You can just extract the words from it, or you can draw a graph or something like that. This example comes from a data journalism workshop that I do, so counting things is more important there than it is for us. But this also shows how to do the same thing with the 100 most common people, right? So now once I've executed this cell, I have a file on my hard drive. in that home directory called, I did it for both people and for time. And again, you can cut and paste this cell and just replace this list with whatever list you previously made, whether it's the nouns or the verbs or the anything else that was a list. You can just put it inside of there. But I made this spreadsheet of times, and I can open this with numbers. All right, going to open numbers. Maybe what's new in numbers? Okay, so now I have this spreadsheet in numbers of all of the most common times that were mentioned. We didn't have that many in this corpus, it turns out. So I'm showing you this stuff because I think this might be helpful. If you have some other tool that you want to work with for recombining these, like if you want to write a P5 sketch or something like that, you can still use Spacey just to extract the vocabulary and then bring that into a different system if you want. But another thing that you can do with this is you could, draw a very bad data visualization. Let's say of like the 10 most common times that are mentioned in romantic comedies. So here's when things happen in romantic comedies. That night and the next morning are by far the two most common times, followed by night, midnight, and the following morning, and one night. Only one instance of a few hours. Questions up to this point? Sure.
Markov converts that CSV file seems contain very many more than 100 words.
Oh, yeah, there's a bug in this code. I forgot to type this. So it's going to have all of the words and not just the top 100. That was a bug, sorry. So I typed in limit between, in the parentheses next to most common, in the cell where it defines the save counter TSV function. Yeah. Now it will just do the top one. I opened it in numbers, but that TSV is recognized by pretty much any spreadsheet program. Excel should open it, Google Sheets should open it. Yeah, so that's a good question. If you change stuff in here, you can save it manually by doing save and checkpoint. It retains the checkpoints once you save it. It does also autosave, but I don't know what the schedule is exactly. So saving and checkpointing often is a good idea. Other questions before we continue? So at this point, I want to show an example of how you might incorporate these things into a tracery grammar. If you cast your minds back all the way to September, when everything was fresh and new, and we weren't as jaded and pessimistic as we are today. We talked about Tracery briefly. So you can use Tracery inside of Python. What I will ask you to do, this is not going to work for you probably. There's a library for Python that implements Tracery, which I wrote. You can install this by, again, going to the terminal window and typing in pip install Tracery, like that. And hopefully that should work. And once you do that and hit enter, and again, I'm not going to hit enter because I don't it won't mess up your computer. It might mess up your Python installation or something because I no longer know what any of these commands are doing on my computer. One day I'm just going to throw my laptop into the sea and start from scratch, and I won't have these problems anymore. but my Python installation on my computer is really, really messed up. But you should be able to type this, hit enter. The installation will be really quick. It's a pure Python library. It doesn't have to compile anything or install a binary, and then you should be able to run this cell without it saying import error. How did that go for people? So again, terminal window, type pip install tracery. It might ask you to say yes or something. And then you should be able to switch back to the notebook and run that cell. So this is going to make it so you can write a tracery grammar, but inside of the Jupyter Notebook. And the benefit of doing that is that if you remember from our original Tracery tutorial, often we had like these really big lists that we just had to type in. Instead, you can take the lists from the Python notebook and just incorporate them into the grammar. So this is making a tracery grammar that has a subject rule, an object rule, a verb rule, an adjective rule, and just grabbing the text that we extracted from our corpus, right? So we're analyzing the corpus, grabbing these parts of speech, and then putting them inside of a tracery grammar, writing particular sentence fragments or sentence patterns, and then printing them out. I might do like a simpler example of this in a second, but I just wanted to create a script that generates new, very short screenplays by essentially making a scene from a location mentioned in these texts, picking character A, character B, some kind of object they're going to interact with, and then a list of sentences. The sentences can be more than one sentence, and then there's a bunch of different sentence patterns. So if you execute that, this is the code that turns those rules into a grammar object that you can do grammar.flatten to generate from that. And these, I have to say, I don't think they're bad. Nora did things became hot. Francesca became reliant. She is jealous, said Mirroring Paris, which is another good name. Who and Katie greeted each other. Who and Katie looked at each other. Who enabled revenge. Revenge became next. That's fantastic. And you can't get this stuff from GPT-2. GPT-2 is just going to be like, hi, this is a thing that Reddit found interesting. And if you wanted to turn this into a novel, here I have it, or into a NanoGenma project, I should say. Here I have it repeating 3 times. If I change that to like 10,000 times, then this is probably 50,000 characters. This is amazing. It's poetic.
What changed in range 3? So we increased that number?
Yeah, I just increased it. When it was 3, it was generating 3 different scenes, right? Another way to do that would be in the origin here, I just have it, the way the tracery grammar is written is it's saying like the sentence might be 2 or 3 or 4 sentences. I could adjust this tracery grammar so that like there were more sentences in here potentially. Yeah, so all of these things right here are things that we found using Spacey in the rom-com text file. So I could incorporate another, like I grabbed the superlative adjectives. I could do that in here too. I could make a super adjectives rule. And then that would be w.text for w in superlative adjectives. So I made a rule for that, and then I might make a sentence format that is like car I.capitalize said you are the super adjective. Like that as a rule. I think that should work. Yeah, so Patrice, that night, Jones became light. George said, "You are the oldest." Who is necessary, said Gidget. Right, so you can incorporate those things back into the tracery grammar. I did that by just like copying this line, making a new tracery rule, whose expansion is this expression that creates a list of strings from that list of spacey extracted things. Questions about that?
Can you go back to where you wrote it in the beginning?
Yeah, so it was all the way up here, back with the parts of speech. Yeah. So if I wanted to do this, we could do like one more exercise with this. So I'm going to go back through the annotation specifications. Let's see what else we have in here. Let's say we want to get all of the ing verbs. So the gerund or the present participle. So like I am singing, that thing in English. So the part of speech tag for that is VBG. So I'm going to capture those up here in this cell. I'm going to say ing verbs equals W for W in words if W.tag underscore equals VBG, like that. And then just run that cell. Now I can grab 12 random ing verbs, like that. Receiving, learning, passing, leaping, seeing, maintaining, kissing, suggesting, demanding, following, telling, slipping.
So the name ing verbs was also in the...
No, this is the variable name. So I could have called this anything. I'm just keeping it similar to what it is so I remember it later. But I could have called this like, you know, good shit. Yeah. And once I've grabbed those from the text, I can then incorporate them into the tracery grammar.
Why is it only this?
Oh, that doesn't matter.
It doesn't
Single
matter.
quotes and double quotes are the same thing in Python.
And then we go back.
Then, yeah, so now we'll go back. Make sure you execute that cell after you're done making the change. Go back down to the tracery grammar, and now I can make a rule that has ing verb. I can call this rule whatever I want. Just copy one of these lines from above and replace where it says superlative adjectives here, or locations or people or whatever, with ing verbs, like that. And then I would add that to one of these sentences. So maybe like car A dot capitalize and car B dot capitalize were ing verb. One helpful thing you can do, by the way, is you can select a bunch of lines and then hit Command/, and then we'll comment out those lines. This is helpful when you're testing a tracery grammar, because I just want to make sure that this sentence pattern works, and I don't care about the rest of the sentence patterns. Whoops, sorry. Yeah, so I made a new sentence pattern that has that ing verb in it. And I misspelled capitalize. And it's just going to say, pick a random ing verb, and then make a sentence that says the first character and the second character were that ing verb. And just to make it easier to debug, I commented out the rest of the possibilities for the sentence, just so I was only ever getting this as the form. Oh, and make sure to put a comma at the end of the line. Otherwise, it's going to mess up when we uncomment it. Yeah. Yeah. So it's exactly the same format, this like bracket w.text. just this name should now be whatever variable you assign that list to. So now when I run this, I'm just going to open up some screen real estate here. I get Jessup and she were preparing, Jessup and she were getting. We keep on getting Lydia in here for some reason. Are you named after a rom-com character?
Wait, that's the last name of the...
That was just a name that was, I don't know if that came from Lydia Jessup in the original
so
text.
Weird.
It's just a weird coincidence.
Maybe
Right, exactly.
I have it this whole time.
So now we get who and he were saying, who and he were uncovering, who and he were hoping. So now we have those ing verbs in our corpus. Right, and now I'm going to uncomment the rest of these lines and see if we can see it in context. Actually, the second one doesn't need to be capitalized now that I think about it. Her brother and him were leaping. Her brother and him looked at each other. In North America later that evening. Questions about that?
I get an error for my
What does it say?
adjectives when I try to do the tracery.
Can I see really, really quick? Yeah, so get rid of that comment at the end. That will go on there and rerun it. Now try it back down Marcos. What did you call this variable at the bottom?
Superlative, actually, not super.
I don't think that matters.
You named it with an S.
Oh, okay. Thank you very much.
There you go. So this is like one way of doing corpus-driven narrative generation. It's sort of a little ham-fisted, but what we've done in this case is gone through an existing corpus of text, analyzed it to extract things from it, and then written a procedure to rearrange them into things that have syntactic structure, right? The overall point of this exercise is to think about how do we generate narrative structure with a computer, right? And in this case, we've sort of cheated a little bit in that we've kind of populated our world with things that we know have particular roles in existing narratives, and also populated our story world with people and locations and stuff like that. The actual structure of the narrative, though, is coming from the Tracery grammar, right? So we've sort of we've developed our story world from the corpus, but not the structure of the stories from the corpus, if that makes sense. So the next thing that I want to show you, and we have just 20 minutes left, so we'll try to move through this fairly quickly, is can we learn narrative structure from the text itself, the structure of the narrative, not just words and portions of the words. So the way that we're going to do that is we're going to develop a language model. A language model is essentially a machine learning model or a statistical model. We don't have to use the word machine learning for this. A statistical model whose role it is to take a whole bunch of text and then answer the question, what word is most likely to come next if given some seed text? So the simplest form of a language model that we can use as a text generator is a Markov chain. It Markov chains have like a really long history in computer-generated text, going back like all the way to 1983. I put here, but I think you could argue that it goes back even further than that. And it's a very simple language model. It does weird things. It's not as impressive as things like GPT-2, but the benefit of it is that you can train it on very, very little text. Like our corpus of just a couple thousand lines of rom-com is going to be enough to train it. So now you need to install one more library, Markovify. You can try running it in this cell. I don't know if it's going to work if you run this in the cell. It'd probably be better to type it at the command line. So again, switch to the terminal. At the prompt, type pip install Markovify. And then hit enter. It's going to install that library. Just makes it simple to make Markov chains.
It says could not find a version that satisfies the requirement of install.
Really? Can I see? Oh, don't do the exclamation point.
Oh, refresh.
Just pip install Markovify. Again, it's a pure Python module. It should be fairly uncontroversial. Oops. Yikes. So I don't have time to go through like the whole spiel of how a Markov chain works. The short version of it is that it, what is the short version of it? The short version of it is that if you give it a bunch of text, it's going to find like repeated patterns of words, and then use those repeated patterns of words as a basis for predicting what the next word is going to be. Maybe I can bring up my notes for another class here and go through it. Yeah, so you might, for example, this is maybe a little bit difficult to read, but imagine you went through a text and you found every unique sequence of 3 words in a row, and then made a list of all of the words that follow that. So this is using the first chapter of the King James Version of the Bible as an example, just because it's like a well-known text. If you went through that text and you found all of the times, like all of the unique sequences of 3 words, you would have something like, well, and the phrase "and the earth" occurs 2 times. Once it's followed by the word "was," once it's followed by the word "brought." This basically means that whenever you see "and the earth" in a text, there's a 50% chance it's followed by "was" and a 50% chance it's followed by "brought." What you can do then is you can use this statistical model to make predictions and chain those predictions together to generate new text. So you could start with "and the earth" and then pick either "was" or "brought" at random, and then you would have the phrase "and the earth was." If you look up "the earth was" in this table, you would find all the way down here. The earth was, in that case, the earth was is always followed by the word "without," so you would add that to the end of the text, and then you would look up "earth was without," which would be out here. Without a comma after it. Without form. Without form also was without form is probably followed by "and." Without form "and" is always probably followed by void, but you can imagine going through that. In some cases, like a phrase will have 2 different options. In some cases, it will only have 1 option. But by chaining together those predictions, we can create a new text that shares statistical properties with the original text, but isn't the same text. Let's just like build one, and that might help make it a bit more clear. So import the Markovify library. This, now we're going back to just the original sentences. We're not going to use spacey for this part. So this cell is making a new list of all of the sentences in that rom-com corpus. And then this builds a big Markov model of all of those sentences. In this case, I don't know if that's all, yeah, all 29,000 in this case, not just the subset. Once you've made the model here, and you'll notice, like, this is another reason, like I said, like the language models that researchers are making today, like GPT-2 and BERT and the big transformer models, will be able to make better predictions, like that maintain coherence, but that's because they're trained on literally like gigabytes or terabytes of text, and they take forever to train, and they emit the same amount of carbon when you train them as like 20 cross-country flights or something like that. A Markov chain, by comparison, doesn't create very coherent text, but it can be trained on a very small amount of text from scratch. You don't have to use a pre-existing trained model, so it's very versatile in that sense. So once you've trained that model in a couple of sentences, and the carbon emission is just related to like how hot your computer got in that very moment, and the energy that it consumed, which in New York mostly comes from nuclear power, although a lot of it still comes from natural gas, so like not as big of a carbon impact, let's say, in training that model. And then this will generate a sentence and then print it out. So this from the Markov model is a new rom-com sentence. She is reading one of the convent, but Darren snaps out of the way to the top genius at Pacific Tech in the workplace, which is a plausible rom-com sentence. Like, if you can imagine, like, going into the writer's room of a rom-com movie and, like, sort of, like, making someone in there distracted, this might be the sentence that they write. The make short sentence method, instead of make sentence, you can limit it to a particular character length. So this will make sure that it's only up to 50 characters long. And then this again would be a thing, and then this, if you specify this tries parameter, you'll notice sometimes when I do this, especially if I decrease this to like 25, a lot of the time it prints none. That's because it's actually like generating sentences over and over and over until it finds one that happens to be less than 25 characters. Sometimes it can't do that, so it prints out none instead. The tries parameter means that it will actually try more times to make that happen. I think by default it just tries like 20 times. If you increase that tries to like 1,000, then it will almost always be able to create shorter sentences, right? Or if you just want to disable, another thing that the Markov chain library does is it checks to make sure that the output is not identical to any of the sentences in the original corpus, just so that you don't like end up generating a sentence and thinking like, oh, that's a really amazing sentence that it generated, and then you realize that that was actually in the corpus to begin with. You can override that though by supplying test output equals false, in which case sometimes you're just going to get exact sentences from the original corpus. So again, this would be like, if you want to take the short way out, you could take this, let's say I want my sentences to be always less than 80 characters, for I in range, let's say 10,000, print all text, make short sentence, and then this could be your NaNoGenMo novel, potentially. Benjamin gives his phone rings. It's Roxana. Brad invites all of Rob's drug paraphernalia. He goes in search of a quarry. Aaron finds solace in the middle of the moon. Meanwhile, Martin is attacked by Tommy and arrested. So it has like this very surrealist quality, like literally surrealist automatic writing quality, where it seems to just be like careening from one subject to the next, like not having any memory of what happened before. And that's because literally a Markov chain, I'm going to interrupt this, it's still going. Literally, a Markov chain only has a memory of like the past n words, where you get to pick the number n. By default, I think it takes into account just the last 2 words. We can increase the number of words that it keeps by the state size parameter. So this is going to create two new Markov models, one with a very small state size of 1, and one with a slightly bigger state size of 4, and we can compare those outputs. So this is generating a sentence from the corpus, just keeping in account one word of context. So you end up getting things that make sense, like maybe just from one word to the next, but don't actually form grammatical sentences. The couple return home of a gym and invites him a man named Connie, Anita, an aspiring lawyer, while the tramp narrowly ahead to see them having sex with their nerves, right? Like that's not, it's nearly grammatical, but doesn't really make sense. As you increase the size of the order, he takes his groceries to the self-help group for autistic adults, you end up getting things that make more sense. The flip side of that is that it's harder to generate these longer sentences that aren't in the original corpus. Like if we move the state size all the way up to like 8 or 9, then we would basically only ever be able to generate sentences that are in the original corpus, because there just aren't that many 8 or 9 sequences of length 8 or 9 words that have more than one word that can follow them in the corpus. If you want to think about things like transformer models or RNNs as advanced versions of Markov chains, you can think of them as Markov chains that have like extremely large state sizes that have been trained on extremely large corpuses. So the trade-off here is smaller state size is more expressive, but less grammatical. Larger state sizes are more grammatical, more sense-making, but less expressive. The other thing that you can do, these have been predicting on sequences of words. You can predict on sequences of characters instead. This adds like a special class to Markovify that will generate based on a character model. And now it's finding patterns in the characters instead of the words. So this is like the word condescendences, which in English is the word that has the most repeated sequences of 2 letters. You can build a Markov chain from that and then generate new words that look like condescendences by analyzing this and then doing that chain. So if we do this with our all of that text, character-based models actually, in my opinion, end up being more expressive than word-based models because it takes advantage of the fact that words themselves have repeated patterns in them. So now we can make, this is with state size 7, with the sentences, she gets to sell his friend and rejoin themselves, the impromptu song, does not know how it all memories of flashback carry into reuniting him because of students.
Are we at word level? Or?
This is character level, yeah.
And so it's totally stateless, so it's just predicting based on the last?
Based on the last 7 characters in this case,
okay.
yeah. So I can increase this. 9 is usually like as high as it makes sense to go. The psychiatry, but she doesn't work. Finding himself to become a werewolf. Yeah, so you end up sometimes with stuff that makes sense, sometimes with stuff that doesn't. But it's actually surprising how much sense you can make with just 9 letters of context. So the example that I want to close out with, if you scroll down further in this notebook, it shows how to train an RNN on this corpus using a library called TextGenRNN that was written by Max Wolf. I also linked to in the syllabus and then also further down in the notes section at the very bottom, Max Wolf's notebook for, not that one, Max Wolf's notebook for fine-tuning GPT-2, and I think Jean did a workshop on that yesterday that some of you went to. So that's another option if you want to make this this project something that has like up to the minute cache, then you can follow that tutorial. I think it's worth just like playing with Markov chains to see what kind of stuff they can make happen. But the thing that I want to experiment with is could we introduce, because a Markov chain can only look at a fixed window of context, what are the ways that we can sort of independently introduce ideas of structure to it? a couple of ideas that have occurred to me and to other people working in this area is like if you took all of these sentences of rom-coms and instead of using the text as it is, went through the text and like replaced all of the character names with just like a placeholder that said like character name or like subject, and then generated the text, but then replaced every instance of that subject with one subject that you've picked at random, then you could make it seem as though it's talking about the same person over and over again. Another thing is when I first loaded this corpus, I kept track of where in the summary it occurred. So like it said, like if the summary has like 10 sentences, this is the second sentence. So what I'm doing here is I'm making a new corpus that only has all of the lines that came first in the summary. So this is the first sentence of a plot summary. So now I have like the things that are setting the scene, basically. In his New York City apartment, a young boy named Josh Morrison stares through his telescope at an object falling through the sky. And then I can make a list of all of the endings, right? So here are 5 random, everyone then Jones Hall notes on stage, right? So now I've made a corpus that's respecting where in the narrative the sentence came from. And then here's another one that is just all of the lines of text that come between the beginning and the end, right? So now I have 3 corpuses, beginnings, middles, and ends. So what I'm doing here in the notebook, just as like one potential idea of how you could introduce your own idea of narrative structure into a generation process like this, is I have 3 separate Markov models, one with just the beginnings, one with just the middles, and one with just the ends. And now I'm going to generate tiny narratives where it starts with one of the beginning sentences, has a sentence generated from the middle, and then ends with a sentence generated from the end. The film is set simultaneously in the middle of $1 million. Peter chases her until Pendergast arrives. Each of the house he had placed strategically around their house. That doesn't make any sense. Shy, soft-spoken Joel Barish and teenagers head for the underdog. That's a very Vladimir Propian sentence, I feel like. When they're at the base, in fact, the vacation is over and Andy makes plans to marry. And we could mess with this in various ways, but that's just an idea of combining a textual statistical model with instructions on how to think of the structure of it based on your own knowledge and your own opinions about how narrative structure works. Questions about this? Sure.
I'm not sure if I understood what state sizes are.
So it's like when we were looking at this notebook, so in this case, I have like every unique sequence of 3 words and then a list of all the words that comes after it. The state size is the length of this thing. So if it's state size 4, then it's every unique sequence of 4 words. If it's state size 5, then it's every unique sequence of 5 words. So you can kind of reason about in your head, like the bigger the state size gets, the fewer of these things you're going to have where there's more than one option to the right, right? So increasing the state size makes it make more sense because you have more things that came from the original text, but it also means that there aren't as many portions of it where it can branch off in different directions, right? Other questions about this stuff? Okay, we're out of time, so I'm gonna stop there, but there is more stuff in this notebook that you can go through. The next time we will meet is going to be on the, not next Thursday because I'm out of town, but the Thursday after that. By that time, I'm hoping that you will have like come up with an overall strategy for your NanoGenmo project and have like a working prototype of the system to generate. And then I can answer questions about those techniques and maybe set you up with some example code if you need some, or otherwise like give you guidance on that part. So I'm going to stop the recording there and then we can answer questions.